Welcome to this presentation about exploring for critical metals using AuScope's Natural Visual Core Library. This paper will present research highlights from the NVCL's critical metals case study sites, how to access the data, and how to get involved in helping Australia to transition to a clean energy future. CSIRO has released the Critical Energy Minerals Roadmap in early 2021, identifying Tier 1 and Tier 2 elements that are critical for the transition of the fossil fuel-based energy sector to a sustainable, renewable energy future. CSIRO Mineral Resources is developing and evaluating cost-effective technologies for characterization of ore and waste throughout the whole mining life value chain. AuScope's Natural Visual Core Library infrastructure program provides high-quality mineralogical and associated geoscience data from Australian mineral deposits. Example drill core datasets of critical metal deposit types that are publicly available via the AuScope portal include LCT pegmatites, nickel laterites, nickel sulphides, tungsten skarns, and rare earth element deposits. This paper presents research highlights from the NVCL's critical metals case study sites. The first example is from the lithium deposit at Greenbushes in Western Australia. We're looking at a drill core C3DD024, which was high-locked scanned by the Geological Survey of Western Australia, and we're looking at diagrams that were produced in the Spectral geologist software. On the x-axis we have downhole plots of lithium from top to bottom, that is lithium geochemistry, and then the mineral matching of pyroxenes and certain scripts that help us to identify spodumene down the drill core. And we can see that the lithium content from geochemistry is very well correlated with the scripts that we applied and also with the automatic mineral matching shown in the middle diagram. We notice that there's a characteristic feature for spodumene in the thermal infrared that we are using that we can now use to track the spodumene not only in this high-logger drill core dataset from the NVCL but in other datasets, such as when we are using handheld FTIRs. So there's a picture of the handheld FTIR on the bottom left, and we have tracked the content of spodumene, also modeled the lithium geochemistry from the handheld FTIR data from various LCT pegmatites from West Africa and Western Australia. So this is all basically based on initial outcomes from the Greenbushes case study data provided by the NVCL. Furthermore, we also had a student working on this Greenbushes dataset, and we found that tourmalines have characteristic thermal infrared spectral signatures in the thermal infrared, and we are now looking into how we can use this information to identify tourmalines of different compositions, which help us to understand the formation of these LCT pegmatites and why some of them contain lots of lithium and others don't, maybe. This next example is about a rare earth element case study from Cummins range. This is an older project that I did together with John Huntington in 2015. And we looked at downhole plots of two drill cores from the Cummins range carbonatite complex. On the left-hand side, we have some diagrams. Downhole is again on the x-axis. At the top, we are looking at the apatite abundance derived from the high-logger data. The second plot from top is the carbonate composition from the high-logger data, and the third diagram from top is the neodymium content, relative abundance of neodymium based on a certain absorption feature at 740 nanometers that we see in the visible near-infrared part of the reflectance spectrum. And at the very bottom we have, for comparison, the geochemistry derived neodymium content, and we see that there's a good correlation between the two neodymium plots, the one derived from geochemistry, the other one derived from the hyperspectral data. So we found that this absorption feature at 740 nanometer is very characteristic, and we can again now apply that to other data sets and hunt for these neodymium-rich samples. Another example I'm going to show here is about how we can use these data collected by the NVCL to develop machine learning methods and apply machine learning methods for nickel sulphide ore deposits. So Lauren Burley from GSWA has put together the diagram on the top left, which basically is based on the nickel-chromium, nickel-titanium ratios, which helps us to understand the chemical composition of different mafic and ultramafic rocks. And we trained the hyperspectral data collected with the high-logger at the NVCL node in WA. We trained those high-logger data with the geochemistry, with those element ratios, and instead of having only a few data points, we then ended up with tens of thousands of data points where we could predict the nickel-titanium, nickel-chromium ratio, and can therefore classify the ultramafic rocks, the different ultramafic rocks down the drill core. The next example is of a nickel sulfate deposit, or a number of nickel sulfate deposits that researchers from UTES have been working on and published this in 2016. They looked at nickel sulfate deposits in the Mount Davies area in the Musgraves block, and we see a diagram that shows the characteristic weathering profile atop these nickel sulfate deposits. And we see that the clay zone and saprolite zone are not very well characterized in this original diagram, but our colleagues from UTES used the high-logger data to get more information about the mineralogy, especially the clay mineralogy of the saprolite and the clay zone, and they identified this certain typical mineral assemblage in the saprolite that develops on top of these weathered mafic, ultramafic intrusions. So this helps us now to, we can make use of this to, when we are trying to explore for nickel sulfate deposits through cover or in the cover. The next example is not really from a drill core data set, but basically we were starting to look into tungsten deposits, like as located as at the King Island deposit in Tasmania. And we collected a number of reference spectra because tungsten minerals, we don't have much there's not much published literature about tungsten minerals and their reflectance spectra in the visible near shortwave, mid and thermal infrared wavelength ranges. So we, as part of the NVCL project, we then acquired some of those scheelite samples, and we found very characteristic spectral signatures of the scheelite, which are quite different to all other minerals that we have encountered before. And so this is now a research we are doing based on the NVCL data, trying to characterize the basic spectral signatures of scheelites, and then maybe trying to find out if we can even map compositional variations of these scheelites down the drill core from the high-logger data. So these are a few snapshots of the research and the findings from the National Core Library focused on critical metals. Of course, AuScope's National Core Library provides provides high-logger data, mineralogy, geochemistry, and so on from drill core data from across the whole continent, as shown on this map, from a variety of mineral deposits, not only the critical metals one, also gold deposits and so forth. But here just some I highlighted some of the locations of these data sets, and I invite everyone to browse through the AuScope Discovery portal and select some of these data sets, and you can download the data, open them in the Spectrogeologist and software package, and start your research in these fields. Also, I invite everyone to look at our webpage of the National Core Library. That was put together with the help of Joe Condon, and we have lots of information about how to access the data, also YouTube training videos. We've got some example data sets that are all publicly available, of course. We got a LinkedIn NVCL group, and of course, again, this AuScope Discovery portal that I invite you to browse and look through the different drill core data sets we have available. Thanks for your attention, and thanks to the whole NVCL project team at CSIRO and at the Geological Surveys.